This is your presenter Asloob Mudassar, and I am presenting slide number 42 of the course on laser physics. Question is sigma the only widely used transition parameter describing the interaction process? The answer is sigma is a very important transition parameter describing the interaction process, provided it is known as a function of nu, that is the frequency of the incident beam. It depends on material parameters, mod square of mu, nu naught the resonance frequency of the material, and gt is a function which we have described earlier. Consider the equation dfx is equal to sigma into capital F. Within the parenthesis we have n2 minus g2 over g1 times n1, and after the parenthesis we have dz. This df is actually a change in flux. When a flux of beam capital F passes through a material having thickness dz, and n2 is the population of the level 2 and n1 is the population of level 1, where g1 and g2 are the degeneracies of the level 1 and 2 respectively, and sigma you know that is the cross section. So this change of flux df is given by this equation, which reduces for the degenerate levels, setting g1 is equal to g2 either equal to 1, or at least g1 can be set equal to g2 for the degenerate levels. So we are setting that the two levels have the same degeneracy, and then in that equation g1 will cancel out will be cancelled out by g2. So we have df is equal to minus sigma, and within parentheses we have n1 minus n2, and then capital F and multiplied by dz. Here we have taken a negative sign common, that's why we have written n1 minus n2 instead, n2 minus n1, and then we have introduced the parameter alpha. So the right hand side of equation number 42.1 gives you df is equal to minus alpha times capital F and dz, where alpha is equal to sigma times n1 minus n2 may be considered another parameter. So you see that here we are introducing another parameter which is alpha apart from sigma. So where alpha is equal to sigma times n1 minus n2 may be considered another parameter to describe the interaction of radiation with matter. If n1 is greater than n2, alpha may be referred to as the absorption coefficient of the material. The explicit form of alpha can be obtained using sigma from equation 41.10 in the following format. And you know that the relationship we have with the sigma, that is we have a relationship over here, you know that alpha is related with sigma, so we can substitute over here the value of the sigma from equation 41.10, which is shown next. So alpha is equal to 2 pi square over 3 n epsilon naught into ch, and then we have u mod square of mu, mod square of mu multiplied by, within the parenthesis we have n1 minus n2, and then multiplied by the frequency of the incident beam which is nu, and then gt of nu minus nu naught. So if you want to see the details of this function gt, you should consult the previous slide, that is the slide number 41. So alpha also depends on the population of the two lasing levels, as obvious from the equation. That is alpha depends on n1 minus n2. So it means it depends upon the population of the two lasing levels. If in a laser system n1 minus n2 changes, then alpha may not be a suitable parameter. So let's integrate equation number 42.1, that is this equation. We arrange df over f on one side, left hand side, and the other parameter on the right hand side as shown, and then we integrate both sides. So we have the integral of df over f is equal to minus alpha times the integral of dz, and then you know that on the left hand side we have the integral which will be in the form of natural log of capital F, and then on the right hand side we have a minus alpha into z plus some constant. And rearranging those terms, we have f prime is equal to capital F times e to the power minus alpha z, where we have used f prime for the terms on the left hand side, and this capital F on the right hand side is used as a replacement of constant. So f prime is equal to alpha times e to the power minus alpha z is given by equation number 42.3. Alpha can be determined if the monochromatic flux could be measured at two planes separated by a distance equal to z. So, using equation given in 42.3, if we want to determine alpha, then we need to measure the flux at two planes separated by a distance z. The distance z will be equal to the length of the material. Alternatively, using equation 42.2, which is this equation, so using equation 42.2, alpha can be measured if n1 and n2 are known. The medium must be in thermal equilibrium. So n2 over n1 should be equal to g2 over g1 into e to the power minus e2 minus e1 over kt. So this is the condition for the two populations, for the n1 and n2 to be in thermal equilibrium. And for this one, for n1 and n to be determined or to be known, we also require the level degeneracy to be known, that is G1 and G2 must be known, and the total population, that is capital NT, which is equal to N1 plus N2, must also be known. Measurement of alpha in this way requires that N1 stands as the population of the ground level. If N2 is greater than N1, alpha may be referred to as the gain coefficient and may be designated by a new quantity G, which is equal to minus alpha, and that is equal to sigma into N2 minus N1. So you see that apart from the sigma parameter, as you know that in the question, apart from the parameter sigma, we also have defined a parameter alpha, and we have described the two ways by which the alpha can be determined. So this is the end of slide number 42.